All right, so for this video, we're going to talk about Coulomb's law and periodic trends and the connection between the two. So the first thing I want to look at is Coulomb's law. This is the equation, and there's an explanation here of what all the parts are. We don't necessarily have to use this equation, so don't get too intimidated by it. And it's actually really simple. We want to understand is what does this tell us about atoms? So Coulomb's law is this equation, and I'm going to walk you through it here real quick. F here stands for, we're going to call this electrostatic force. Okay. And electrostatic force is the force of attraction between a positive and a negatively charged particle. So, this is attractive force between something that's positively charged and something that's negatively charged. Okay, this equation works for all positively and negatively charged particles or objects, but for our purposes, we're mostly going to think about electrons and neutrons, electrons and protons, obviously. K here is a constant, so we're not really going to worry about that too much. Constant. R is distance or radius, but really it's distance. So it's a measurement of distance. And then Q1 is, Q1 and Q2 are the charges of the positive and negative particles. Okay. So what we want to try to think about here is we have two variables. We've got charges and we've got distance. Those are the two variables that we need to start kind of figuring out. So let's just do a quick example. We'll run some numbers through this and we'll see what we come up with. So let's just say we have a +1 positively charged particle and a -1 negatively charged particle. And I'm going to make up a unit of distance. It doesn't really matter what they are because we're just kind of plugging in some number. And we're going to say that they're one, I'm going to use meter just because it's a unit of measurement, but it really doesn't matter. There's a lot of math involved here. It doesn't matter. They're going to say they're 1 meter apart or 1 centimeter maybe, which is way more than a centimeter, but that's fine. Okay, so 1 centimeter. So what is the force of attraction between these two charges? Well, we're going to kind of abstractify this a little bit, but let's just plug some stuff in here. Q1 and Q2 represent the charges. So those are going to each be 1. So rewrite this here real quick so we can see exactly what we're doing here. So that's going to be, we'll just kind of ignore this, this KE thing. So we can kind of just plug it in or just leave it alone. It's fine. We're going to go 1 and -1. And actually, I forgot we need to do absolute value around this. So that way we get rid of the negatives. Okay. And we're going to divide that by the distance. The distance is 1 squared. So in this particular case, the attractive forces, which are measured in in newtons, I think, if I remember correctly. But again, it doesn't really matter. The force of attraction between these two, one's positive, one's negative. They're definitely going to want to come closer together. There's going to be attraction there. 1 times 1, -1 is -1, but absolute value is just 1. 1 squared is 1. So it's just going to be 1. Okay, so that's our first scenario. So let's test out some of these variables. What would happen if we increase the distance or decrease the distance? Let's increase it. I think that's kind of fun. Let's bump that up to 2. Same particles, just a +1 and a -1 particle. Now we're at 2 centimeters. So what do we think is going to happen to the attractive forces? Well, from a mathematical standpoint, distance squared, we're taking, to get the new force, we're going to have to divide by the distance squared. So if they're further apart, the number on the bottom is going to be bigger, which means that we're dividing by a bigger number, which means we should end up with a smaller number. So let's just confirm that real quick. So I'm just going to use that same equation from before. So this time we have, once again, we've got a +1 charge and a -1 charge. We're going to absolute value those. And we're going to have to divide this by 2 squared. So 1 times 1, -1 is -1, but absolute value is 1. And then 2 times 2 squared is 4. So that's going to be 1/4 or 0.25. So that is definitely less than 1. So we can say that the further apart these two charged particles are, the less attractive forces they're going to have with each other. Okay, what happens if we change the charge? So let's go back to our original example. Let's go back to 1 centimeter as our distance. And let's make this 2+ instead. And let's make this one, we'll keep this one the same as just 1-. So let's see about what happens in this scenario, what the attractive forces are like. So this time we're going to have 2 positive times 1 negative, absolute valued, and we're still going to divide that by 1 squared. And that is going to be equal to, let's see, 2 times 1, -1 is -2, but absolute value is 2 divided by 1 squared, which is just 1, so that's just going to be 2. So looking at this, when we compare to our original, when we doubled the distance, we reduced the force by a quarter. When we doubled one of the charges, we doubled the force. That's exactly what this mathematical equation is telling us, right? The force is directly related to the charges of the particles. The force is inversely and also exponentially related to the distance. So if we have two particles, the distance between them is going to be really, really important. And the charge will also be important, but less so, less dramatically. So let's think about this. This is all well and good, but hey, why the heck do we care about this in chemistry? Well, we care about this in chemistry because atoms are made of charged particles. And we know that atoms have a very particular structure. They always have a positively charged nucleus, and they've got these little negatively charged electrons all around them. And there is a force that holds them together. They're connected to each other in that particular way. So they are drawn towards each other. There's some amount of force. It's electrostatic. There's electrostatic forces that hold them together. So I use the word electrostatic because think about like electricity and static electricity. So if two things are of opposite magnet charges, it's a magnetic attraction, which is similar, but this is technically a little bit different because magnets aren't charged. They just have like charged ends, sort of. It's a whole thing. But yeah, so it's an electrostatic force is what we call that. So what we want to kind of think about here is we're interested in how each individual electron is attracted to the nucleus and how strong that force is. If that force is really strong, the electron is more likely to stick around. And it's going to have effects on the properties and the properties of the atom. Yeah, a lot of things about that. Depending on exactly which atom it is, the distance from the electron, the distance from the nucleus, and the charge of the nucleus are the biggest concerns. We're never really concerned about the charge of the electrons because the electrons are just kind of floating around, and each individual electron has its own separate interaction with the nucleus. The fact that there's 2 electrons here doesn't really matter. They're each a specific distance from the nucleus, and each one of these forces are the 2 separate forces that we're concerned about in this case. So let's do a quick summary of this. One moment, please. Pulling up the PowerPoint slide, something for you to write in your notes. Okay, so what is the effective charge? The higher charges means more in terms of Coulomb's law in a general sense that we've just summarized for you. Higher charges mean more attractive electrostatic forces. Lower charges mean less electrostatic force. Charge and force are directly proportional. The effective distance. The more distance between charged particles means less attractive forces. The less distance means more attractive forces. These are therefore inversely proportional. I didn't mention in these, but you can also add in that it's exponential as well. So it will make small changes in distance will make a really big difference, whereas small changes in charge will make less of a big difference. Still a difference, but not as dramatic, not as much. Okay. So let's talk about this in terms of periodic trends. There are three different factors that we need to explore when it comes to periodic trends. And I'm going to show those to you right now. I'm just trying to decide how to do it. Yeah, I'm going to do it this way. We'll take a look at your notes. What you're going to have to be able to do is these are the three. We're going to write some stuff on the periodic table in just a second here. There are three different properties of atoms. There's atomic radius, electron affinity, and ionization energy. And what I'm going to do for this kind of section is give you two different atoms or a couple of different elements, I guess, atoms of elements. And I want you to compare their atomic radii, their electron affinity, and ionization energy. So tell me which is the highest and which is the lowest based on periodic trends. What I want you all to do is you're going to be able to write some of these trends on this table, this periodic table in your notes. And you can also, we're also going to write an explanation for each of these trends for why is this true. So let's kind of go through them one by one. We've got atomic radius is the first one. Let me think about this for just a second. I'm wondering if, no, let's do it this way. I've got a different idea. We'll come back to the notes, but I'm going to give you some examples from the packet, and I think that will help explain it. So the first thing is atomic radius. So your atomic radius is your distance from the nucleus to the valence electrons. So let's go through a couple of examples, and we'll see which elements maybe have what the trend is going to be for this. I have pulled. Let me see what we got here. Okay, taking a look at packet 7, periodic, oh, we don't need that periodic table. We got this little one right here. I have pulled questions. We're going to be kind of use question 1, 2, and 3. And 4. Yeah, I got to go through this. Okay, it's not too far. So we're going to use answer 1, 2, and 3 from the unit packet. This is page 4. So we're going to kind of use these as examples to explain, and then we'll go back to the notes. So this has circled the element with the largest atomic radius and put a square with the lowest atomic radius. The second one we're going to talk about ionization energy, and then we're going to talk about electron affinity, and then we're actually going to skip number 4, but we'll get to that. So we have 4 different elements. We've got copper, potassium, nickel, and bromine. So let's find those on our periodic table. I'm just going to kind of circle them with a pencil. So we've got copper is right here, nickel is here, bromine is here, and potassium is here. So all of these elements are on the same row. Yes, row, not column. So I've drawn a little picture of each one of these. Okay. So our first thing that we'll take a look at these. So I've got copper here. I didn't put all the electrons in because we only really care about the valence for the most part. But all of these, their valence electrons are on the 4th orbital, the 4th shell. Okay. They each have a different number of valence electrons. And I also put the number of protons. So we're going to go through each of these trends and try to figure out what the deal is with each one. So let's start off with radius. Okay, and we're going to rank these in order from which is the biggest to the smallest radius. Okay, so Atomic radius is the distance from the nucleus to the valence electrons. So looking at these drawings, it would appear that each of these should have the same radius, right? They all have electrons on the same shell. And that's generally, there's an element of truth to that. That's a good pun. There's a little bit of truth to that, but that's not actually true. What's going to happen is the electrons, according to Coulomb's law, are going to be attracted to the nucleus. So each of these electrons has a -1 charge. Okay, just going to write those in real quick. So we'll just kind of focus on one electron from each. Each of these is going to have a -1 charge. And that is going to pull them in towards the nucleus. Some of these electrons are going to get pulled in a little bit more, and some of them are going to get pulled in a little bit less. So we need to try to figure out which ones are going to get pulled in the most and which ones less. So the actual forces we have to look at are between the nucleus and the valence electrons. So according to Coulomb's law, there's two factors that are involved. There's distance and charge. Because these are all these electrons are on the fourth shell, the distance should be pretty much the same. Sorry, just give that a second. However, the charges are not. All of the electrons have the same charge. They're all -1, but the nucleus is not. This one, what is this one? Bromine has a plus 35 and potassium only has a plus 19. So this means that bromine is going to have a lot more pull. The charge is, the force is going to be a lot stronger. So that's going to pull the electrons in, and it's actually going to make the radius a little bit smaller. So in terms of which way are we ranking them? We're ranking these from the largest atomic radius. The ranking is actually going to be based on whichever one has the smallest positive charge. So potassium is going to go first because it has a smaller charge. So therefore, the electrons are pulled in less. The next one would be nickel. Sorry, I'm just writing these down here at the bottom. I'm going to draw you some more pictures here to explain it. And copper. And finally, bromine. Okay. And again, it's like this. I'll draw you guys a little quick picture. Got our nucleus of each of the four, right? And we got our four. So potassium on each of the levels, the electrons don't have quite as much force. So they're kind of pulled away a little bit. Here, it's a little bit tighter, kind of a smaller radius. This looks really silly, doesn't it? Even smaller here. And even more so here. So the actual radii, and again, it's because of individual electrons and how much they're being drawn inwards. Okay. So potassium is going to have the largest radius, and bromine is going to have the smallest, and nickel and copper in between. So let's take a look at our periodic table and see what that has to say, what that tells us. If we look, we're going to see that potassium, these are all in the order of the periodic table. And that is not on accident. That is just a consequence of the periodic table being the way it is, and that's how we just understand chemistry. So the general trend here is that as you go across the periodic table from left to right, radiuses decrease or they increase this way. What about up and down? So we've done kind of on the row side. Let's check out a few others. Let's look at the next set. I've got oxygen. No, I didn't. I chose. Perfect. Okay. Sodium, rubidium, francium, and hydrogen. So let's just circle those. I think the atomic radius is pretty clear here. I got hydrogen. I've got sodium. I got rubidium and francium. I think in this case, it's pretty obvious. Straight up orbital levels. You know, they're all in different orbitals. So clearly for radius here, for the radii, if we're going from biggest to smallest, it's definitely francium, then rubidium, and then sodium, and then hydrogen. And if we look at our periodic table, yeah, francium, rubidium, sodium, hydrogen. Okay, so the atom elements with the biggest radius is going to be francium. The element with the smallest radius is going to be probably like helium. It's very, very tiny. Okay, so let me go back to we'll go to the PowerPoint and you can fill out that relevant, the notes for that. Okay, so this is the increasing radius. You can label that on your periodic table. The explanation is kind of what we just talked about. So if you're going up and down the periodic table, it has to do with the shells of the electrons. As you're going across, where they should all be on the same shell, it all has to do with the charge of the nucleus. So sorry. You all can remember it by these trends, but when I ask for an explanation, which I will, the actual explanation has to be involving distance and charge of the distance from the nucleus and charge of the nucleus needs to be referenced. So I could say something like the radius of cesium is bigger than barium because barium has an extra proton, so it has more attractive forces and pulls the electrons inward and makes the radius smaller. Something like that. Okay, so that's atomic radius. Let's talk about the next couple. We'll go back to our overhead. Okay, the next thing is electron affinity and ionization energy are kind of the opposites. So let's kind of go through them simultaneously a little bit. Electron affinity is how much energy is gained when you add an electron. So this is how much the affinity that the atom has for more electrons. So this is like ionizing to become a positive, to become a negatively charged atom. Ionization energy is how much energy you need to remove an electron. So this is kind of the opposite. So the trend is going to be very similar. It's how much attraction, how much force does that nucleus have on any new electron that might be on any of its valence electrons, whether it's adding a new valence electron or one of those valence electrons being taken away or going away. So let's go back to our examples and we'll see what we can think of. Okay, so let's look back at copper and potassium and nickel and bromine, and let's talk about electron affinity. So which one of these do we think is going to have the most force, the most highest electron affinity, holding on to that electron? Well, once again, we're back to the same problem. We need to figure out, technically all these electrons, the distance should be sort of vaguely similar. We kind of know they're not. We know that the radius is because of what we understand about radius, we're pulling those in just a little bit tighter. But again, the force is all determined in this case by the charge. So they're all essentially relatively similar distance from each other. They're all in that fourth orbital. But the charge of the nucleus is going to, again, pull them in just a little bit tighter. The closer and tighter and stronger that force is, the more attractive force from that nucleus, the stronger it's going to be able to hold onto those electrons. So in fact, the order is exactly the same. So electron affinity. Here, I'll write this down here so you guys can see it. Electron affinity. The highest electron affinity in this case, it's going to be opposite. The 35, the positive 35 of that nucleus is way stronger than the positive 19 of that, like almost twice as strong. Pretty crazy. So in this case, the electron affinity is going to be bromine is first, then copper, then nickel, then potassium. Okay, so the exact same logic. Let's take a look then at our other example of sodium and rubidium and francium and hydrogen. So looking at these ones, which ones are going to have the most attractive forces? Well, these ones are a little trickier. So let's really go through them. We need to figure out what is the attractive force that's really going to hold on to these electrons between these four atoms. So there's two factors here that we have to deal with. Each of them has a different distance from the radius, or from the center, from the radius of the atom is different, but they also have different charges. So how do we know what's more important? So like, for example, hydrogen only has a +1, but that electron is super close, that valence electron. Francium is a +87, that's huge, but its electron is really far away. Okay. This is where we can go back to Coulomb's law. If we go back to Coulomb's law, if you'll remember the squared here, distance always beats out charge. Because of this squared, the distance has a much bigger impact than the charge. The first thing is always distance. So if you have more electrons in between it's actually called a nuclear, it's called a nuclear shielding, which is a whole nother topic. But yeah, if you have a whole bunch of electrons here in the way and so much distance, the +87 doesn't really matter that much. The distance is the biggest factor here. So in terms of electron affinity, the hydrogen actually is going to beat out everything else, even with its just measly +1 charge, because the distance is so close. That electron is so close. That one has the highest. The next is sodium, then rubidium, then francium. Okay. All right. So going back to our notes, let me pull these up for you. You can draw this on your periodic table. Electron affinity is the opposite. So something like helium is going to have an extremely high electron affinity. It has two protons, and the two electrons are the electrons, its valence electrons are so close by. So compared to hydrogen. So hydrogen is going to have a bigger radius and less electron affinity because it has half of the nuclear charge, but the electrons are still pretty close. There are actual numbers that we can put to these, which we did in a lab. It gets kind of complicated when you start adding different factors in, but I'm only ever going to ask you to look at either the rows or the columns. Okay, the lower you are on the table, the more shells of electrons you've added. So you're adding more and more and more distance and more just like electron interference blocking some of that charge to some extent. So the electron affinity is going to decrease as you go down the table. Okay. All right. Let's go with the last topic for us here. Let's talk about ionization energy. So ionization energy is how much energy it takes to remove an electron. So let's go to our first set of examples. Okay, back here. Let's throw in ionization energy. So which one is it going to be really hard, really difficult? So we're going electron affinity. Did I do that? Yeah, we went from high to low. Okay. Yeah. So which one's going to be really hard to remove an electron from, and which one's going to be pretty easy? This is kind of the opposite of electron affinity, or it's the same kind of. It's the other side of the coin of that relationship. So whichever one has the highest electron affinity, it's also going to take a ton. Oh no, ionization energy. Sorry, it's not removing. It's adding. Sorry, never mind. Nope, it's removing. Electron affinity is gaining new ones. Ionization energy is losing them. Yeah, that makes perfect sense. Okay, yeah, we're good. So how much energy is it going to take? Sorry, I'm just going to go back here. It's gained when you add an electron. Yeah, it is adding electron. Okay, just making sure. Sorry, guys. So if you're trying to remove electron, it's going to take a ton of energy to remove an electron from something that really has a strong hold on it. So it's actually going to be exactly the same as electron affinity. So for bromine is going to have a much tighter hold on its electron with that plus 35, potassium less so. So same thing. Okay, so here's your these are your answers, by the way, for 1, 2, and 3 on your packet. Ciao. Pretty cool. Okay. How about for this other example? Well, okay. Hydrogen's electron is being held pretty tightly. There's a lot of force holding it, so it's going to take that same amount of force to remove it. 1 second. Sorry, lights. Whereas francium, its electron is so far away and there's not that much holding it. It's pretty easy to just snag an electron off of francium. So again, same order as before. Okay. The periodic table, these trends will really help you to remember all of this, but the actual logic, you don't even really need the periodic table. I mean, not exactly. You just kind of have to understand the principles behind it, like this distance and charge thing. But the periodic table helps to organize all that information. So let's go back to those notes. And I think we're just about done here, but we'll maybe might do one more quick example, although we've just done 2 examples already. Okay, so ionization energy, same thing. It's the exact same thing as electron affinity. So it's how much energy you have to exert in order to pull an electron away. Okay. Looking back at your packets, this is I think that's all we need to do. We should double check, make sure. Oh yeah, we're totally good. Looking back at the packet, we can answer some questions. So there's a couple of things I forgot. Okay, so for 1 through 3, we can answer we've already answered these. The atomic radius one, what did we say? Atomic radius was potassium has the largest and the smallest was bromine. The highest ionization energy was bromine and the smallest was potassium. And the same thing was true for electron affinity. So those are all kind of the same. Those are all those answers. And explain, this is the explanation part. This is the part where we need to say something about how the bromine has more protons with, similar distance than potassium. Okay, so the more protons, similar distance thing is kind of what we're looking for there. I did not do 5, 6, 7. Oh, and number 4, anytime you see electronegativity, just skip it. Just don't do that one. Electronegativity is another concept. It's really basically the same thing as electron affinity and ionization energy. So it would actually be the same answers, but we don't have to worry about that. That comes with bonding. We'll deal with that more in AP Chem. Okay, we ended up also doing 9, 10, and 11. Again, you can skip 12. So 9, 10, and 11, we said for 9, the largest radius was going to be francium and the smallest was hydrogen. The highest ionization energy is hydrogen. The lowest is francium. Same thing with electron affinity. Put a square man with the lowest. Oops, it was the opposite. Sorry. Circle, square, circle, square. And this one is because of distance, more distance between nucleus n valence electrons in francium means less electrostatic forces, or something to that effect. You're going to find yourself repeating the same answers over and over again, because those are basically the trends. Those are all the trends. So do not tell me that one is to the left or right of the periodic table of each other. The periodic table is arranged in the way it is because of these explanations, not the other way around. The trends will just help you, and using the periodic table will help you to know what's happening and kind of keep it all straight in your head. So that's this is on page 5, by the way. If you look there's just a few more questions that go into page 6. Once again, you'll be able to skip anything with electronegativity. So you can skip 16 and you can also skip 20. This one at 21 is a little bit of an extra kind of a bonus one. I would say it's more of a bonus. That's going to be something you may have to think about. So what happens if you have an ion? So think about whether you're adding more electrons or removing more electrons, and what kind of effect that's going to have. How will it change the radius of the neutral atom? And kind of think about that one. And we can always talk about that in class. Okay, I don't think I have any specific videos for you on this, but those were a couple of examples from the worksheets. And that is pretty much it when it comes, we're going to kind of move on away from atoms and move into bonds. And I'll see you for that next video then. Thank you.